Calculate the chi-square statistic, degrees of freedom, and p-value for a chi-square test based on data in a two-way table. Perform a chi-square test for homogeneity, a chi-square test for independence, and choose the appropriate chi-square test based on a context. That's the overall idea. Right, the two sample Z procedures of Chapter 10 allow us to compare the proportions of successes in two populations or for two treatments. What if we want to compare more than two samples or groups? More generally, what if we want to compare the distributions of a single categorical variable across several populations or treatments? We need a new statistical test. The new test starts by presenting the data in a two-way table. Two-way tables have more general uses than comparing distributions of a single categorical variable. They can be used to describe relationships between any two categorical variables. Start by comparing distributions. Market researchers suspect that background music may affect the mood and buying behavior of customers. One study in a Mediterranean restaurant compared 3 randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the numbers of customers who ordered French, Italian, and other entrees. And this is their observed data. We have the type of music and entrees ordered in our two-way table. First, we're being asked to calculate the conditional distribution in proportions of the entree ordered for each treatment. So when no music is playing, the distribution of entree orders was French of 0.357, Italian 0.131, and other 0.512. When the French accordion music was playing, we have the distribution of entrees orders as the French of 0.520, Italian of 0.013, and other of 0.467. Lastly, when we get our Italian string music, the distribution of entree orders was French of 0.357, Italian of 0.226, and other of 0.417. So this is just our distributions, right? Our conditional distributions for the observed data. We can make bar graphs of this data to compare it further, just visually compare, and we should be able to see some differences. Also recall, in the digital version of the exam, you will not be asked to draw graphs or anything because there's no way for you to submit that type of thing. You might be provided a graph to make a comparison with, but you will not be asked to draw one. So we're now being asked to write a few sentences comparing the distributions of entrees ordered under the 3 music treatments. We have the type of entree that customers buy seems to differ considerably across the 3 music treatments. Orders of Italian entrees are very low, 1.3% when French music is playing, but are higher when Italian music, 22.6%, or no music, 13.1%, is playing. French entrees seem popular in this restaurant as they are ordered frequently under all music conditions, but notably more often when French music is playing. For all 3 music treatments, the percent of other entrees ordered was similar. Right. So we have that. Just basic comparison. The problem of how to do many comparisons at once with an overall measure of confidence in all our conclusions is common in statistics. This is the problem of multiple comparisons. Statistical models or statistical methods for dealing with multiple comparisons usually have 2 parts. Number 1 is an overall test to see if there is good evidence of any differences among the parameters that we want to compare. Number 2, a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. We only have step 2 if we find significance in step 1. There's no need to do a follow-up analysis if you fail to reject the null hypothesis. The overall test uses the familiar chi-squared statistic and distributions. Now we're getting into the nitty-gritty. All right, so we need expected counts to get our chi-squared statistic. Chi-squared test for homogeneity begins with the hypotheses. The null hypothesis is that there is no difference in the distribution of a categorical variable for several populations or treatments. And the alternative is that there is a difference in the distribution of categorical variable for several populations or treatments. We compare the observed counts in a two-way table with the counts we expect if the null hypothesis were true. We always calculate expected counts under the assumption that the null hypothesis is true. Does anyone need a moment to write anything down from this screen? So consider the expected count of French entrees bought when no music was playing. We have 99, the total from the row of French, divided by 243, right, which is the table total amount of entrees ordered, times 84, the total number of entrees ordered when there was no music playing. Basically, we're finding out the expected count is kind of how we've calculated it previously. It's the kind of the proportion of that type of entree ordered overall, which is the 99 divided by 243. We had 99 French out of 243 total, times the number of entrees ordered with the given treatment. Right, the values in the calculation are the row total for French wine, French entrees, the column total for no music, and the table total. We can rewrite the original calculation as 99 times 84, row total times column total, divided by table total. We get 34.22. Any questions about how we find an expected count for a particular cell of the table? So then we have the following. When we're finding expected counts, when the null hypothesis is true, which is always the assumption when we're finding expected counts, the expected count in any cell of a two-way table is the row total times the column total divided by the table total. And then we have our conditions for performing a chi-square test for homogeneity. We have the random 10% in large counts conditions, as we have seen previously. I'm not sure why this has an error in it. And this is a picture, so I can't fix it, but in the random condition for performing a test of homogeneity, we must have random samples that are independent from the two populations or multiple populations we're comparing, or groups, or randomly assigned treatments. This is what we have in this example. We have the three treatments that have been randomly assigned, making a randomized experiment. 10% in large counts are the same, as we've seen previously. In large counts, all expected counts are greater than 5. Would anyone like a moment to write anything down from this screen? And then, as we have previously, we need to find our chi-squared statistic. Same way we did for goodness of fit, we compare the observed counts with the expected counts using the statistic. Chi-squared equals the sum of observed minus expected squared divided by expected. This time the sum is over all cells, not including the totals in the two-way table. So here we have our observed counts, our expected counts. We're going to use these to find the chi-square statistic. Here they are again. And then, for example, for the French entrees with no music, the observed count is 30 orders and the expected count is 34.2. The contribution to the chi-squared statistic for this cell will be 30 minus 34.22 squared divided by 34.22, and we get 0.52. For this particular set of tables, this comparison, we will have 9 things, 9 cells contributing to the chi-square statistic. All right. The chi-square statistic is the sum of 9 such terms. Notice they're not listing all 9. It is sufficient to show that you know the formula to use, such as shown here. Give the first couple, do the little dots here, and then do the last one, and then just have the total. It's not even absolutely necessary to show like each individual term or each component, unless you might need that later on. Okay. There's ways to have the calculator find our chi-square statistic. We'll see how to do this tomorrow when we do our practice problems. That is much, much more efficient than doing all these by hand. This could become very time consuming to find each of these values one at a time. Anything I can clarify about this finding of the chi-squared statistic? Earlier, we started a significance test of the null hypothesis that there is no difference in the true distributions of entrees ordered at this restaurant when no music, French Quarter music, or Italian string music is played, versus the alternative that there is a difference in the true distribution of entrees ordered at this restaurant when no music, French Quarter music, or Italian string music is played. Again, I want to point out the only difference between these two statements is one says there is no difference and one says there is a difference. After that is a copy-paste of the same statement. Once again, we have our observed counts. We already checked that the conditions were met. Our calculated test statistic is chi-squared equaling 18.28. We're going to use table C to find the p-value. Then use your calculator, chi-squared CDF command, to find the same value again. It will be slightly different, obviously. Because the two-way table has 3 rows and 3 columns that contain the data from the study, we use a chi-square distribution with degrees of freedom equaling 3 minus 1 times 3 minus 1, which is otherwise 2 times 2. That is 4 to find the p-value. We'll get into why we do this in just a moment. In the small little section of table C that we have here, we have degrees of freedom 4, right? The value of chi-squared equaling 18.28 falls between the critical values 16.42 and 18.47. Right, it is much, much closer to 18.47 than 16.42. Chances are we'll get something closer to 0.001. Corresponding p-value is between 0.0025 and 0.001. Sorry, again, there's a typo there. Using the calculator, we can use the command chi-squared CDF. We have a lower bound of 18.28, the chi-squared statistic we found, an upper bound of just a large number because there is no upper boundary to this. We just need it big enough, right? And degrees of freedom 4. And this gives 0.0011 as our p-value. Okay. And to get to this chi-squared CDF command, you need to use your calculator and hit second vars, and that gets you to the distributions menu. And you'll just scroll down until you get to the chi-squared CDF command. Again, we'll show you that tomorrow as well. Is there any questions here about finding our p-value? So next, it's asking us to interpret the p-value from the calculator in context. Notice the next question is, what conclusion would you draw? Interpreting the p-value and making a conclusion are two entirely separate statements. They are not equivalent. They are not asking for the same thing. Interpreting a p-value is saying, what does this probability represent in context? Right, so we have assuming that there is no difference, right? Assuming that the null hypothesis is true. In the true distributions of entrees ordered in this restaurant when no music, French Quarter music, or Italian string music is played, there is a 0.011 probability of observing a difference in the distributions of entrees ordered among the three treatment groups as large or larger than the ones in this study. Right. So again, there's a 0.011 or 0.1% chance that we see a distribution with this large of a difference between the three treatments as we did in this study if the null hypothesis were true. Very, very, very small chance. What conclusion would we draw? Because the p-value 0.0011 is less than our default alpha equaling 0.05, we reject the null hypothesis. We have convincing evidence of a difference in the distributions of entrees ordered at this restaurant when no music, French Quarter music, or Italian string music is played. Furthermore, the random assignment allows us to say that the difference is caused by the music that's played. So again, we have that condition of random assignment that allows us to make a better inference, so to say. You can say this is possibly caused by the difference in music type. Is there anything I can clarify about these two statements and the difference between them? Here's the rundown for the chi-square test for homogeneity. Suppose the conditions are met. You can use the chi-square test for homogeneity to test the null hypothesis. There is no difference in distribution of a categorical variable for several populations or treatments, versus the alternative that there is a difference in the distribution of a categorical variable for several populations or treatments. You would start by finding the expected count for each category, assuming that the null hypothesis is true. Then calculate the chi-squared statistic, as we've seen previously, where the sum is over all cells, not including totals, in the two-way table. If the null hypothesis is true, the chi-squared statistic has approximately a chi-square distribution with degrees of freedom equaling the number of rows minus 1 times the number of columns minus 1. So once again, the degrees of freedom is based on the number of categories, not the sample size. Right, so when we're doing chi-square tests, whether it's goodness of fit, test for homogeneity, or test for independence, which we'll see next, the degrees of freedom is always based on the number of categories. Right. The p-value is the area to the right of chi-squared under the corresponding chi-square density curve. So we need a moment to write anything down from this screen. We can do a follow-up analysis on the example we just saw. Right? The chi-square test for homogeneity allows us to compare the distribution of a categorical variable for any number of populations or treatments. If the test allows us to reject the null hypothesis of no difference, we then want to do a follow-up analysis that examines the differences in detail. Again, if we fail to reject the null hypothesis, there's no need to do a follow-up analysis. Right? But because we did reject the null hypothesis, we can do one. We'll start by examining which cells in the two-way table show large deviations between the observed and expected counts. Then look at the individual components to see which terms contribute most to the chi-squared statistic. We have this data table here that shows the expected counts below the observed counts, and then the chi-square contribution below the expected counts for each of our 9 categories or 9 cells. Looking at the output, we see that just 2 of the 9 components that make up the chi-squared statistic contribute about 14, almost 77% of the total chi-square, equaling 18.28. Right, French music and Italian food, and Italian music and Italian food. Right, and those have the largest deviations. We are led to a specific conclusion. Orders of Italian entrees are strongly affected by Italian and French music. That is seemingly to create the largest differences and the largest contribution to our chi-squared statistic. So that would be the follow-up analysis. Are there any questions about the follow-up analysis? So when we get to relationships between categorical variables, this will be chi-square tests for independence, right? This is when we're checking for an association. Another common situation that leads to a two-way table is when a single random sample of individuals is chosen from a single population and then classified based on 2 categorical variables. Suppose we randomly sampled 100 students from the school district. Then after we selected a random sample, we then categorized them by their gender, male or female, and then their subject preference or something like that in classes. We would then be trying to find an association between gender and subject preference. Right, and that is a test for independence. The test for homogeneity would be if we separated and independently selected a random sample of males and female students, and then check to see if there is a difference in preference in their subject preferences. That would be a test for homogeneity. All right. We'll get some practice with that tomorrow as well. So in this case, our goal is to analyze the relationship between the variables. Our null hypothesis is that there is no association between the 2 categorical variables in the population of interest. The alternative hypothesis is that there is an association between the variables. 10% and large counts condition for the chi-square test for independence are the same as for the homogeneity test. There is a slight difference in the random condition for the 2 tests. A test for independence uses data from 1 sample, but a test for homogeneity uses data from 2 or more samples or groups. Right, that is the major difference. We randomly sample from a single population and then categorize. That's test for independence. Independently randomly sampling from different groups or different populations, and then categorizing by some variable is a test for homogeneity, or can lead to a test for homogeneity. And again, we have our conditions here, random, 10%, and large counts. We have our basic rundown on our chi-square test for independence. Right. Suppose our conditions are met, you can use the chi-square test for independence to test the null hypothesis that there is no association between 2 categorical variables in the population of interest, versus the alternative, there is an association between 2 categorical variables in the population of interest. We'll start by finding the expected count for each category, the same way as we did for the previous two-way table. Calculate the chi-square statistic, the same way we did for the previous example, right, where the sum is over all cells, not including totals in the two-way table. This whole next part is the same. If the null hypothesis is true, the chi-squared statistic has approximately a chi-square distribution with degrees of freedom equaling the number of rows minus 1 times the number of columns minus 1. The p-value is the area to the right of chi-squared under the corresponding chi-square density curve. the calculations that are performed if you're doing a test for homogeneity or a test for independence are exactly the same. You define the expected counts the same way for both. You find the chi-square statistic the same way for both. You determine the p-value the same way for both. The major difference is the context of the two tests. One is testing for a difference. Is there a difference between the distributions of the two populations for this single variable versus checking for an association between two variables within a single population? And so that affects how you write your hypotheses and then ultimately how you write your interpretation and conclusion. The middle part, the calculation part, is the same. So are men and women equally likely to suffer lingering fear from watching scary movies as children? Researchers asked a random sample of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. More than 1/4 of the students said that some of the fright symptoms are still present when they are awake. The following table breaks down these results by gender. So again, they randomly sampled from a single population of college students. They then broke down this data by gender and whether or not they're experiencing fright symptoms. So we have two categorical variables that we're comparing. And this is our observed counts. They then used some fancy software called Minitab that we don't have access to, but they do, and they have it shown here. Minitab output for chi-square test using these data is shown below. So again, we have observed, expected, and chi-squared contribution for each of the 4 cells. This software also outputs our chi-square statistic, 4.028, degrees of freedom equaling 1, and our p-value is 0.045. Right, we get degrees of freedom 1 because we have 2 rows and 2 columns. 2 minus 1 is 1. 1 times 1, 1. So this is our data that we'll be able to use. Explain why a chi-square test for independence and not a chi-square test for homogeneity should be used in this setting. And again, we're assuming the conditions have been met. The data were produced using a single random sample of college students who were then classified by gender and whether or not they had lingering fright symptoms. The chi-square test for homogeneity requires independent random samples from each population. Is there anything I can clarify about the difference between these two tests? We want to state an appropriate pair of hypotheses for researchers to test in this setting. So we have that the null hypothesis is that there is no association between gender and ongoing fright symptoms in the population of college students. And the alternative hypothesis is that there is an association between gender and ongoing fright symptoms in the population of college students. Once again, this is almost word for word the same 2 statements. We're only changing no association and an association. So that's it. Copy paste. Which cell contributes most to the chi-square statistic? In what way does this cell differ from what the null hypothesis suggests? And recall the null hypothesis is that there is no association. And we have men who admit to having lingering fright symptoms account for the largest component of the chi-square statistic. Right, 1.883 of the total 4.028. We can see that the next closest one is less than half of what that particular cell is contributing. Far fewer men in the sample admitted to fright symptoms than we would expect if the null hypothesis were true. So this is how it differs from the null hypothesis. Right. The null hypothesis basically is saying there shouldn't be this big of a difference between the expectation and what we saw if there was no association. So next, we want to interpret the p-value. Remember, our p-value is over here, 0.045. In context, what conclusion would you draw at alpha equaling 0.01? So they've given us the significance level to use. But again, this is not, the first part is not making a conclusion, it's interpreting. The second part is writing a conclusion. If you only provide the conclusion, you're not completely answering the question. If gender and ongoing fright symptoms really are independent in the population of interest, essentially if the null hypothesis is true, there is a 0.045 chance of obtaining a random sample of 117 students that gives a chi-square statistic of 4.028 or higher. Because the p-value, now this is answering the second part of the question, this is the conclusion. Because the p-value of 0.045 is greater than 0.01, we would fail to reject the null hypothesis. We do not have convincing evidence that there is an association between gender and fright symptoms in the population of college students. Is there anything I can clarify about this answer to that question, about interpreting and writing a conclusion? And that brings us to the end of the presentation. All right. So we saw two new chi-square tests for homogeneity and independence. We discussed how they're similar and different. Essentially, they both use the same calculations, which is why in the second example we didn't go through the calculations. But the way that they are interpreted and the way they're set up in their hypotheses, slightly different. All right. And so we've done all these things. We'll get some practice with this stuff tomorrow. We'll do a Desmos activity, which will again give us a little bit of review at the beginning, and then we'll do some practice problems, working with some of this stuff. That's what we'll do tomorrow. Does anyone have any questions, comments, concerns? Anything else you need support with today? All right. Well, then with that, I hope you have a great rest of your day. We'll see you all tomorrow for our practice with section 11.2. Have a good day.